Okay, this is part 2 of the lecture on section 4.1 from Math 311, a course in linear algebra at Western Illinois University. Okay, so in the last video we found out what eigenvalues and eigenvectors are, and some of their geometric interpretations of some of the examples. We want to get to a little more theory and a little more that will lead to a little more standardized way to find these eigenvalues and eigenvectors. So we'll start off with this fact that if A is an n by n matrix and lambda is a complex number, and of course that means that lambda could also be a real number, then the following statements are equivalent. First, that lambda is an eigenvalue of A. And then number 2 says AV equals lambda V for some non-zero vector V in Rn. Notice that of course 1 and 2 are equivalent because number 2 is basically the definition of an eigenvalue. Number 3 says the null space of A minus lambda I is not equal to 0. And 4 says that A minus lambda I is not invertible. Now, if you recall back on the last chapter from the fundamental theorem of invertible matrices, they said that if a square matrix being invertible is equivalent to its null space being 0. Well, the flip side of that says if a matrix is not invertible, then its null space is not 0. So the only difference here is that the matrix we're talking about is A minus lambda I, where this I is the identity is IN. Okay, it's the, if you want to put an N here, so that these computations make sense. These expressions make sense. Okay, so 3 and 4 are equivalent. 1 and 2 are equivalent, and the only thing we have to convince ourselves is that 2 and 3 are equivalent. And I think that's kind of, well, let's see, to show 2 implies 3. 2 means that AV equals lambda V. Well, that means that AV minus lambda V is 0. And this means that AV minus lambda INV is 0 because, lambda is just a constant, right? And the V and IV are the same thing. And we can factor out a V, so this will be AV minus lambda IN. Oops. A minus lambda INV has to be 0. And I said because we're saying that we're requiring V to be non-zero for some non-zero vector V, then this is equal to 0 for some non-zero vector V, okay, which is the same thing as saying that the null space of A minus lambda IN is not 0. Okay, all right, and everything else, we can reverse directions. This implies this, which implies this, which implies this, which implies this. So everything. So these are all equivalent, and this is 3. Okay, so 2 implies 3. 2 and 3 are equivalent, and that basically proves this. So to show that lambda is an eigenvector, or is an eigenvalue, that's saying that A minus lambda IN as a matrix is not invertible. And of course that is equivalent to saying its null space is not 0. It also means its rank is not n, and all these other nice things from the fundamental theorem of invertible matrices. Okay, couple other things. Definition of an eigenspace. If we know that, of course, eigenvectors are not, for each eigenvalue, you can have many eigenvectors. You can get, for example, if AV equals lambda V, Okay, you can multiply BV by any constant you want. Let's say K. A times KV is going to be lambda times KV. Okay, so KV will be an eigenvector as well. Okay, so there are infinitely many eigenvectors, and of course if we take all the vectors v that satisfy this equation, AV equals lambda v, that is all the eigenvectors of lambda along with a zero vector, then this is called the eigenspace of lambda. Okay, so the eigenspace of lambda is just all the eigenvectors of lambda plus the zero vector, and E lambda is this eigenspace is a subspace of Rn. And the reason for that is that E lambda is precisely the null space of A minus lambda In. Okay, and we know that from the last chapter that the null space of any matrix is a subspace. Okay, so that's important. All right, next. We're now going to just focus on the case of 2 by 2 matrices, because in the, if you recall, there was a very nice way of determining, computing the inverse of a 2 by 2 matrix, and of course that finding the inverse also means determining if it's invertible or not. And we had this not coincidentally, we had this expression called the determinant of a 2 by 2 matrix of ABCD is AD minus BC. And we say that this matrix was invertible as long as this determinant was not 0. And then the flip side of that says that this matrix is not invertible if and only if the determinant is 0. Okay. So now the matrix, we're worried, we're not really, we don't want to, so if A is equal to the matrix A, B, C, D, then A minus lambda In is going to be this matrix. And we want to know, well, what is it? And if you're not quite sure about that, lambda In is going to be lambda 0, 0, lambda. Okay, so you take the difference of these two matrices here, and you get this. And then this is not invertible if and only if the determinant of this matrix is 0. So what is this? It's just this entry times this entry minus this entry times this entry. So A minus lambda times D minus lambda minus BC. That we want that expression to be 0. And remember, we don't know what, as of right now, we don't know what lambda is. And if we treat lambda as a variable or an indeterminate, this is going to be a characteristic polynomial. This is going to be a polynomial lambda. This is going to be, if you multiply this out, you'll see it's going to be something times lambda squared, something times lambda squared plus something times lambda plus something. Okay, so it's going to be a second degree polynomial or a quadratic polynomial in lambda, and this is what we call a characteristic polynomial of the matrix A, B, C, D. This is important because the roots of the characteristic polynomial are going to be the eigenvalues. All right, the eigenvalues of the matrix, and that's because those are the values that make this matrix not invertible. So we get, summarizing this, we get if A is a 2 by 2 matrix, then lambda is an eigenvalue of A if and only if lambda is a root of the characteristic polynomial of A. All right, now one little thing, what happens if lambda is a complex root? Okay, so we're going to, if lambda is a complex number but not a real number, then the eigenvectors will not be real. So you can, right now it's going to be a little ambiguous. You could get away. We don't want to do a whole lot with complex numbers in this course, at least not right now. So we could say, so if the eigenvalues are complex, I'll accept you you can say that there are no, you can just say there are no real eigenvalues. All right. Okay. We don't want to really concentrate on complex numbers in this course, even though that they are in higher advanced linear algebra classes. You won't be able to escape complex numbers. Okay. All right. And then all these examples in this class, I think all the eigenvalues will be real. Okay. Wanted to finish up with an example of how we might do this. So let's say our matrix A is the matrix 5, 6, 4, 3. Okay. Let's say we want to find the eigenvalues of this matrix. Okay. So A minus lambda I is going to be 5 minus lambda, 6, 4, 3 minus lambda. Okay, so the determinant of A minus lambda I is going to be 5 minus lambda, 3 minus lambda, minus 6 times 4, that's 24. Which will be, if we multiply this out, this is lambda squared minus 8 lambda plus 15 minus 24, which is lambda squared minus 8 lambda minus 9. So that would be the characteristic polynomial of A. And to do this, so now to find the eigenvalues, we set this equal to 0. Now, this like in the previous example, we have a quadratic equation, and we can use a quadratic formula if we want, where A is 1, B is -8, and C is -9, and you can use the quadratic formula, or in this case, you can see it factors relatively nicely. This factors is lambda minus 9 and lambda plus 1. Okay. It did not factor nicely in the other example where we had we had 1 plus the square root of 5 and 1 over 2, but for that it didn't work out. They worked out, but they were not nice. Couldn't factor it like this. So you can always use the quadratic formula, but sometimes you can, if you're good at factoring, you can do it this way. And the advantage of this way is you can set each factor equals 0. And you get lambda equals 9 and lambda equals -1. So these are going to be the eigenvalues. Okay, now let's find the corresponding eigenvectors. Okay, so what we're going to be doing is now we're going to be plugging in these values for lambda in here into this matrix and see what we get. So in the case where lambda equals 9, we get 5 minus 9, that's -4. 6, 4, and 3 minus 9 is -6. Okay, so this is now A minus lambda I, where lambda is 9. And what we want to do is the eigenvectors are going to correspond to the null space of this matrix. Okay. Now in this case, you could go ahead and do reduced row echelon form for this, but you can see that these rows are going to be multiples of each other. And you're going to see that once you do the calculations correctly, the resulting calculations won't be that bad. See, we're trying to find these vectors x, y such that this is equal to 0. So the first one tells us that -4x plus 6y equals 0. The second one tells us that 4x minus 6y equals 0, and that's not too bad, is it? Because we can see that this basically tells us that 4x equals 6y. This also tells us 4x equals 6y, and we can divide by 2 and we'll get 2x equals 3y. So that tells us if we let x be anything we want, as long as 3y equals 2x, that will get an answer. So if let's say if x equals 1, well, actually, we can let we can get that. How about we do it this way? We let x equals 3/2 y. So in this case, we can let y be anything. So we can let y equal 1. So if y equals 1, we get x is 3/2, and that will be a perfectly good eigenvector. Or we could just multiply the stuff by 2 to clear out the denominators, and we'll get 3, 2. Okay. So either one of these are perfectly good eigenvectors, but the eigenspace will be the span of 3, 2 for lambda equals 9. Okay. For the other one, lambda equals -1. Let's see what we get. So here we have 5 minus -1. That would be 5 plus 1. That's 6. And then this is 6. This is 4. And then 3 minus -1 is 3 plus 1. That's 4. Okay. So we get this. And once again, we can see one row is going to be a multiple of the others, which is what we expect it would be, because this is a 2 by 2 matrix, and the rows, if this matrix is not invertible, then the rows are going to be linearly dependent, and the only way that can be linearly dependent is if they're multiples of each other. So if we set the xy, this equal to 0, 0, and we get 6x plus 6y equals 0, and we get 4x plus 4y equals 0, and this basically means that x equals -y. Right? We divide both sides by 6, and we take something to the other side, we get this. We get the same thing if we use this equation. So we can let y be anything we want. We can let it be 1. So we get -1, 1 is a perfectly good eigenvector. So in this case, the eigenspace would be the span of -1, 1. Okay, you could also make this 1, -1. That's the same span. Okay. All right. So you can check that these actually work. You can check that 5, 6, 4, 3 times -1, 1. This will be -5 minus 6. -5. Right, -5 plus 6, that's 1, and -4 plus 3 is -1, which is -1 times -1, 1. Okay, so that does work. All right. The main thing here is finding the eigenvalues is the important part. You find that by finding a characteristic polynomial. Once you find the characteristic polynomial, it's just a matter of plugging these eigenvalues into a minus lambda I, and then find the null space, which we know how to do. All right, see you next time.